Hi everyone, my name is Nikos Giavellis and I'm here with Nofar Karmeli to present to you our work on the orders of conjunctive query answers that allow efficient direct access. This is joint work with Wolfgang Gatterbauer, Benny Kimmelfeld and Mirek Ridewood. Let's start with an example.
Hi, Nikos. I have these tables with information about my employees. Which employee has which role, how much I paid a role in a particular period of time, and how much I paid them for their travel expenses. And I would like to get some statistics on how much I pay an employee a month, like the median, a box plot, or the details of everything I pay, sorted by how much I pay in pages where I can access any page arbitrarily. Now I can see one way of doing that, and it is to compute this conjunctive query that joins these relations and these as answers. And then for every employee in a month, I get the salary that I paid them and the travel expenses. And then I can sort these answers by the sum of the salary and the travel expenses. And then I have direct access given an index to every answer, and I compute everything I want. The problem with this is that the number of answers here can be much larger than the size of the input or the number of answers that I want to actually access. So is there a way of doing it directly without materializing all of the answers?
That's a very interesting problem of ours, so let's try to formalize it. Let's call it the ranked direct access problem, which is defined by a query and an order on the query answers. The input is a database of size n, and our goal is to have an algorithm that, after some pre-processing, can achieve direct access. This means that given an index k, it is able to access the query answer at that particular index in the sorted array of answers, which is sorted according to our order. Our goal is to achieve quasi-linear preprocessing and polylogarithmic access time, which makes sense because we can't avoid linear preprocessing and logarithmic factors don't have much of an impact in practice. Nofar, what are the possible orders you want to support?
Well, first of all, I think lexicographic orders can be interesting in many scenarios. This means that along with the query, I will give you an ordering of the free variables, and I would like the query answers to be sorted lexicographically according to that ordering. But sometimes not all free variables are relevant for the ordering I want to achieve. I will call this partial lexicographic order, and then I'll give you an ordering of some of the free variables. And for example, I want to get all of the answers first sorted by address, then to break ties by salary, and then I don't care how you break the ties, it can be arbitrary. Another type of order I would like to support is sum of weights. Then every domain value of every free variable has a weight, and we want to sort the answers by the sum of weights.
Is there a connection between these two?
Yes, in a way, sum of weights is stronger than lexicographic order because it can simulate any lexicographic order. As an example, if we want the partial order address salary, we can assign weights such that address always dominates salary, and then sorting by sum of weights is equivalent to sorting lexicographically. So let's see some background now on related problems.
If we look at related work, there has been work on enumeration, where the task is to return the query answers one after the other. This is a special case of direct access, where we first access the first index, then the second index, and so on. It has been shown that enumeration with or without a ranking is possible with linear preprocessing and logarithmic delay if and only if the query is free connex, which is a particular condition on its structure. This equivalence holds under some standard complexity assumptions. I also think there has been some work on direct access, right?
Right. So unranked direct access was called in the past random access or the jth answer problem. And there have been several solutions proposed for this problem. All of these solutions, by the way, do have some restricted order support. They all have an underlying lexicographic order, whether they state it or not. But this lexicographic order is restricted by the structure of the query that is being used as part of the algorithm. For example, a join tree. So these algorithms cannot support any lexicographic order. And what we would like to do is, first of all, to support additional lexicographic orders, but also to identify exactly which lexicographic orders can be supported. So we said we cannot even do enumeration when a query is not free connex, so we can definitely not do ranked direct access in these cases. Can you remind everyone what free connex is?
Yes, of course. A query is acyclic if it has a join tree, and the join tree is a tree where the nodes correspond to the atoms of the query, and for every variable, the nodes that contain the variable are connected. A free connex query has an additional requirement, which roughly says that there is a connected part of the tree that contains exactly the free variables.
So now let's see an overview of our results, and let's start with full lexicographic orders. So I remind everyone that we're interested in quasi-linear preprocessing time and polylogarithmic access time, and now we want to know which queries and orders we can achieve within these time bounds. For queries that are not free connex, we said we cannot do that, and this holds under some assumptions. We have no self-joins and some hypotheses in fine-grained complexity, and these assumptions are also required for the lower bounds that we will see later. Within free connex queries, we have a characterization that depends on the existence of disruptive trios. Query is tractable if it has no disruptive trio, which is 3 variables, where the last one out of the 3 in the order we want to achieve shares atoms with the previous 2, but the previous 2 do not share an atom. As an example, this query here, if we want it in the order V1, V2, V3, it has a disruptive trio, so it is intractable. But if we swap V2 and V3 in the body of this query, we get this query that has no disruptive trio, and therefore it is tractable. Now, for those of you who know the notion of elimination order, requiring no disruptive trio is like requiring that the order is an elimination order. Our algorithm builds upon an approach that was proposed in pods of last year. We defined something called a layered join tree, which is specialized for an ordering we want to achieve, and we apply this approach on it. And we also have some modified access routine that allows us to support additional orders. For the hardness results, we show that if there is an efficient direct access algorithm for a query with a disruptive trio, then it means that there is also an efficient enumeration algorithm for queries that are not free connex, and this is why this is not possible.
All that here is for full lexicographic orders where all the variables are in the ordering. What happens for partial lexicographic orders?
Well, for partial lexicographic orders, we show that the partial order is tractable if and only if we can extend it to a tractable full order. That is, we're given this ordering of some of the free variables, we treat it as a prefix, and if we can extend it to an ordering of all of the free variables where there is no disruptive trio, then these are exactly the tractable cases, and we characterize when that happens. So in addition to having no disruptive trio, we require L-connexity, where L-connex is very similar to free connex. So with free connex, we said that we want a subtree of the join tree that contains exactly the free variables. And now we require the same, a subtree that contains exactly the variables for which we care about the order. As an example, this query here, and let's say we care about the order of V1 and then V2, but we do not care about the order of X, even though it is a free variable, then this join tree shows that it is L-connex. But this query, on the other hand, is not L-connex, and in fact, you can see that if we say that we care about X and it's the last one in the ordering, then we do get a disruptive trio. What about sum of weights?
For sum of weights, we also established a dichotomy, and we saw that the tractable cases are the queries where all the free variables are contained in one atom, which is of course a very restricting condition. As an example, Q1 here has all its variables x, y, z in the R atom, and so it's tractable. The algorithm is, in that case, is actually trivial because there is a relation that contains all of the answers. But on the other hand, query Q2 has variables x and z that do not appear together in an atom, and that makes it intractable. For the hardness proof, the main idea is that with binary search, we can find if there is a query answer with a specific weight. And we use that in a reduction from the three-sum problem, which asks for three integers that sum up to 0.
So you said that there are many queries that are intractable. Is it because even one direct access call is hard, or because we require supporting several direct access calls after one preprocessing phase?
That's an excellent question, and to answer it, we explore another problem, which we call selection. In the problem of selection, there is no preprocessing, and we simply measure the time it takes for a single direct access call. Tractability in this case is defined as quasi-linear time for one direct access. We establish a dichotomy for the class of full conjunctive queries and sum of weights orders, and we find cases where selection is tractable for both sum of weights and lexicographic orders, even though direct access is intractable.
So to conclude, we show a characterization of direct access with respect to lexicographic orders and with respect to sum of weights. And we also looked into the problem of selection, a single sum of weights, and show that sometimes selection is tractable even though direct access is intractable.
For future work, there are many cases for selection which we haven't explored in our paper, and there are also other interesting questions such as more expressive queries, different types of orders, and different time bounds. Thank you for listening.
Thank you.